Then the author says, we shall discuss the method of exhaustion presently. No, we shall not. If you want to know more about exhaustion, get the book, but we will continue from here because he doesn't dive in that very instant. The benefits of the intensive mathematical activity of the 5th and 4th centuries BC were reaped by the mathematicians of the Hellenistic period. Among the numerous figures of this period who were important in mathematics, 3 important ones were Euclid, Archimedes, and Apollonius. Little is known about the life of Euclid, although probably more people have read some version of his Elements than have read any other scientific book. Elements is supposed to be the most widely read scientific book in human history. We know that he flourished about 300 BC, or as Proclus says, in the time of the first Ptolemy. Proclus goes on to repeat one of the stories about Euclid, quote, "And further they say that Ptolemy once asked if there was in geometry any shorter way than that of the elements, and he replied that there is no royal road to geometry." I've heard that was said to a king during the Renaissance too, and it probably was. Besides the famous Elements of Geometry, a number of other mathematical and physical works are credited to Euclid. As the passage from Proclus suggests, Euclid's great achievement lay not in presentation of original material, but rather in his able synthesis of geometrical knowledge. His Elements replaced the several earlier collections, or elements, composed by mathematicians of the 4th century. The form and organization of the Elements are worthy of some note, for such form was quickly adopted in most of the mathematical and physical treatises of the Hellenistic period. And remember, Hellenic, then Hellenistic. And it survived into medieval and modern times. The reader who has looked at the mathematical principles of Isaac Newton will appreciate its debt to Euclidean form and organization. Now, I'm just going to read the 5 postulates, or just a quick little blurb about them. The 5 postulates of the first book are the most noteworthy, since they really define the whole character of the space and geometry under consideration. The first postulate permits us to draw a straight line from one point to any other point. It's as easy as that. The second allows us to extend that line indefinitely from either extremity. The third allows us to draw a circle from any center at any distance from the center. The fourth asserts that all right angles are equal, and the fifth, which is the famous parallel postulate, tells us under what conditions straight lines will intersect. The genius of Euclid in recognizing this 5th postulate as a postulate and not attempting formal proof has often been remarked. I don't know the extreme significance of that, but apparently he recognized that it's fact available to the senses, not to be explained. Now, a lot of mathematical work and scientific stuff has been done in the last 2 centuries. Non-Euclidean geometry, you've heard of that. Quote, "It's well known that in the 19th century, geometries that were not Euclidean were constructed on the basis of denial of one or more of the postulates." So just check out those postulates, see if you can deny any of them, because you have to get to non-Euclidean geometry. A generation or 2 after the time of Euclid, there lived the most distinguished mathematician of antiquity, Archimedes, from 287 to 212 BC, approximately. It is inferred, but not surely, that he studied at Alexandria with the successors of Euclid. We know him to be a native of Syracuse, where he spent some time in the service of its ruler, Hiero, H-I-E-R-O, and where he was slain in its siege by Roman troops in 212. Fascinating story there. Fought the Romans off, bloody, savage, but the Romans eventually won. His fame as an engine builder is preserved in the fanciful accounts of Archimedes given by Plutarch in his Life of Marcellus, the Roman general who conducted the siege of Syracuse. Quote, this is from Plutarch, The Life of Marcellus, translation of Bernadotte Perrin, London, 1917. "And yet even Archimedes, who was a kinsman and a friend of King Hiero, wrote to him that with any given force it was possible to move any given weight, and emboldened, as we are told by the strength of his demonstration, he declared that if there were another world and he could go to it, he could move this. Hiero was astonished and begged him to put his proposition into execution and show him some great weight moved by a slight force. Archimedes therefore fixed upon a three-masted merchantman of the royal fleet, which had been dragged ashore by the great labors of many men, and after putting on board many passengers and the customary freight, he seated himself at a distance from her, and without any great effort, but quietly setting in motion with his hand a system of compound pulleys, drew her towards him smoothly and evenly, as though she were gliding through the water. Sounds like an exaggeration to me, but apparently he did some sort of demonstration with pulleys. End quote from Plutarch there. Plutarch goes on to describe Archimedes' use of wonderful military engines in the defense of Syracuse, which, however, did not save either Syracuse nor Archimedes, for both fell before the Romans. In spite of these great mechanical talents, we are told further by Plutarch, Archimedes held the mechanical arts in disdain. Quote, regarding the work of an engineer and every art that ministers to the needs of life as ignoble and vulgar, end quote, and devoted his greatest efforts to theoretical studies. We are told further by Plutarch that Archimedes devoted his greatest efforts to theoretical studies, such as geometry. In view of the general non-critical nature of this account, there is no good reason to accept this statement as reflecting the actual attitude of Archimedes. Nevertheless, it is true that his great efforts were in mathematics and in the theoretical and mathematical aspects of statistics and hydrostatics. We can glean something of Archimedes' subject matter from a recital of the titles of his works. So here we are. On the sphere and the cylinder. On the measurement of a circle. On the conoids and spheroids. The sand reckoner. On spirals. On the equilibrium of planes. On floating bodies. On the quadrature of the parabola, and on the method. In much of his mathematical works, he concerned himself with finding the areas and volumes of special curved surfaces and solids, relating them to the more readily obtained results for a triangle, a rectangle, a cube, or some such figure. His most powerful tool for proof consisted of a highly developed procedure of reduction to absurdity, combined with the method of exhaustion. The fundamental idea of the method of exhaustion is that one inscribes and or circumscribes regular figures within or without a figure for which the formulation of the area or volume is sought. Then, in regular fashion, the areas or volumes of the inscribed or circumscribed figures are increased or decreased till the difference between the unknown area or volume and the inscribed or circumscribed area or volume is less than any given quantity. Now I pause there to say we're just about to get a glimpse into an ancient Greek fallacy in mathematics, which you will know as Zeno's paradox. And this is a glimpse into how one way it affected their thinking in mathematics. In this method, we do not say that the increased or inscribed figure or decreased circumscribed figures ever actually reaches the limit. It doesn't reach that limit, namely the unknown figure that we're looking for, because the Greeks thought that this would involve them in fundamental difficulties about the infinitely small. So they were so worried about where can you draw the line. They thought it's arbitrary to ever draw the line on dividing something infinitely small. Or, like for example, Archimedes is running towards the tortoise, and he gets halfway there, and then half again, and 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 if you have to keep dividing it, at what point do you say we're done dividing and has reached the tortoise? Same with the arrow that's going towards the tree. If you do have to keep dividing it half and 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 half, when does it reach the tree? And the answer to that is, anytime you're measuring something, dividing it however far you are, you don't have to divide any further than the quantity or the specific units you're measuring with or using. That's it. It goes to your context and no further. If you're looking at who got to the line first in the race, You don't have to go any further down than the thickness of the race rope or something like that. You don't have to go